Thanks a lot for the invitation to come speak here. It's yesterday was I learned a lot from all of the talks, and thanks for turning out at, as you said, 9 a.m. on a Saturday. So I guess I'm this set of talks this morning is the general theme, I guess, was networks and other forms of complex data. So since I'm trying to give the opening overview talk and sort of inspired by the two overviews yesterday morning, I sort of wanted to stick in that spirit of really trying to survey a bunch of questions. And so I tried to pull together questions that we're asking with the kind of data that we're finding online, both network and content data, to sort of touch on a bunch of things. Because I think one potential value from these kinds of meetings is that, exposing all of you with the sort of amazing range of techniques you have at your disposal to some of these questions could lead to some fruitful things. So I'm going to focus on a set of problems that arise in the online world from online content, online social networks. To sort of frame this, in some sense, the issues they present are new, and in some sense, they have very deep roots in a bunch of literature. So, I think if you had asked me and my friends in grad school, in the early 90s when the web first emerged, how do we think about the web? We would have drawn for you a picture like the one on the left, that the web was becoming this vast universal library of all human knowledge. And I think the kinds of questions we asked for the first 10 years of the web really reflected that metaphor, right? That the basic units of analysis were pages and hyperlinks. We were trying to extract information from this corpus. We were looking at the links as associations. Something sort of amazing happened in this 2004-2006 period where the experience of the web really did fundamentally change. In a sense, people stepped out from behind their web pages and began interacting more directly through social media, right? In a 2-year window, you saw the creation of Facebook, Twitter, YouTube, all of these things. And so suddenly a second metaphor began competing for our attention, this metaphor of the crowd, where we wanted to understand events in real time, and the basic units of analysis were these individual perspectives, right? The individual tweets, social contagion became an issue. Now, this tension between the library and the crowd, it would be presumptuous to think that we had somehow invented this opposition. You can, in fact, go back to the middle of the 20th century and find people who really had articulated this tension quite clearly. In computer science, we all know this article. I'm not sure if it's as familiar in economics, but in 1945, right at the end of World War II, Vannevar Bush, who was very high up in the US science funding establishment, wrote this article in the Atlantic Monthly entitled As We May Think. If you haven't seen it, it's worth reading. It's one of these sort of frighteningly prescient descriptions of what he thinks the information infrastructure for the next 50 years should look like. And he describes it quite concretely. He says there's going to be documents, and these documents are going to have these associative links between them. And if some document reminds you of some other document, you're going to follow that link, and you're going to blaze these trails of associations. He imagines a search industry that's going to help us search these documents. It's, as I said, it's quite frightening. It wasn't entirely luck, as in, given that he was directing a lot of the US science funding apparatus, he actually steered a lot of resources in to try and make this happen, but it's amazing how much it did happen. Now, so this is the library metaphor, but there's also the crowd metaphor, right? So if we go back to some of the early work in the diffusion, what became the enormous area in sociology, the diffusion of innovations, some of the early people in that, like Elihu Katz and Paul Lazarsfeld, who studied the effect of disruptive technological change on the political process, right? But in their era, that disruptive technological change was radio and TV, right? And they found that, in fact, radio and the printed page often had only negligible effects when they would interview someone on what they thought affected their vote decision. It was often talking to the other people, right? Your friend was a voracious consumer of news, and you talked to them, and that's where you got your opinions from, right? So this sort of library versus crowd tension. And I think we see all of this in big online social networks, right? So if we think about what we have now, something like Facebook, it's a bit too easy to sort of imagine that Facebook is simply a place where we go, we spend time, we hang out with friends, we just sort of, to think of it as an essentially superficial activity, because there are a few respects in which it's actually fundamentally changed our connections to information and to other people. Let me mention two of those, which will kind of frame some of what I'll talk about. I'll talk more about the first in the first half of the talk, some questions arising there, and then the second in the second half of the talk. But clearly, if you think about it, Facebook and Twitter, we've sort of signed on to a system where social ties are forming one of the main transport mechanisms for the information we get, for information, opinions, behaviors, and so forth, right? Just as the sociology literature on the diffusion of innovation sort of tells us it should operate. That's, of course, always been true of offline social networks, but this has really made it, that much more powerful and non-local. It also, of course, it's a development that's maybe less surprising to people who've studied offline social networks and where that's their basic conceptual framework. For computer scientists like me who thought about the web, again, for the first 10 years of the web, we thought the idea was that you go and you seek out the information. The information sits there inert, and you're going and finding it. And in that sense, social media is quite a surprise because it really brings us, much more in alignment with the way information flows in the offline world. The information actually is curated by your friends. It seeks you out. The second, and I would argue more subtle change that social media has brought about is this kind of algorithmic assistance in maintaining your social ties over time. And I'll get to this in the second part of the talk, but sociologists also tell us that we have a wide range of tie strengths. We have strong ties to close friends, close colleagues, people with whom we have these very strong affective connections, and then a wide range of weak ties to people that we know less well. And of course, the uncertainty in our relationships to the weak ties is precisely what makes them so valuable for this transport mechanism for information, right? They have access to information that we don't. That was Mark Granovetter's original strength of weak ties argument. The point is, if you think about people of, say, my generation and older, most of our weak ties, they're present for a while and then they completely vanish, right, over time because it's just very hard to maintain them, right? So if I think about the people I knew in childhood, the people I went to high school with, all the way up to the age of 18, on the day I went off to college, most of those ties began to just evaporate, and in some very real sense, they're gone now. With effort, I could reconstruct one of them. I could find that person, get back in touch with them, but there's no real sense in which I am. And we often don't think about this subtle, but I think powerful thing that Facebook has really radically changed that for people who are in this new generation, that it requires a certain energy investment on your own to maintain a weak tie, but Facebook can maintain it at very low intensity forever. So every 2 to 3 years, if this person gets married, gets a new job, whatever, you'll hear about it through your newsfeed. And that's a very, that requires algorithms working in the background to rank and filter what is the content that you're receiving, right? These concentric circles around you that say, some people you want to hear from, you want to hear what they had for dinner last night, you want to see the photo of the dessert from last night, the whole thing. But some people, it really is every 2, 3 years you'd like to hear from them. And in that way, you're maintaining all these different concentric circles, right? That's somehow cognitively too hard for human beings to do unassisted, but that's exactly what Facebook is very good at doing, and it's actually caused this significant change. And so if we really want that to happen, we actually need algorithms that are figuring out how do I manage one person's network neighborhood, their connection with the world. So that's the second kind of big theme. Okay, so having that's the kind of organizing structure for what I want to talk about. I then want to sort of delve in and actually pick some of the concrete questions that come up when we ask, about these sorts of things. So the social transport of information. So lots of information gets shared online. I think you can all imagine your own examples just to make sure we have kind of one to look at. This is one that David Libanow and I started studying actually in early 2003. At the time it was very topical. It was a chain letter petition protesting the then impending US invasion of Iraq, which happened 2 months later in March 2003. And it sort of looks the way online appeals for action still look now. It begins with a kind of message, containing things that are sort of true. And then it has an appeal. Please forward this message, sign at the end of the list, and then you'll collect this petition. This was one of the most successful internet petitions of all time in the pre-social media era. And so the idea is these things trace paths out through the social network of the world using electronic communication. And there are these very natural tree structures that you can build from that, right? So at the root is the very first person who originated the petition maybe, and they pass it to some friends, they pass it to some friends, and it just keeps spreading out. And the natural tree structure is that if node W acquires it from node V, then V is the parent of W in the tree. Now the tree elides richer structure. Maybe you got it from 2 people, maybe, obviously there are many independent starts, so it's actually a forest of trees, not just one tree. But it's amazing how many different domains have something like this, right? So sharing links via blog posts, when one blogger invokes another one, that hyperlink tells me who their parent is in the tree. cascading product recommendations. When there's a coupon that one person will collect if they socially recommend it to another, I know who gets the coupon. That defines the tree. The chain layer petitions that we studied, phrases being passed through news and blogs, and certainly on Facebook there's an explicit reshare mechanism. So you see that this person reshared that person. That too defines the tree. Again, many different roots. So it's really many trees sitting next to each other. Similarly, many platforms actually grow through cascading invitations, right? So LinkedIn, there's a roughly 200 million node forest of trees that basically consists of each root is somebody who just walked up to the LinkedIn site and signed up, and then all the invitations that they sent. If you accepted their invitation, you're now a descendant of them in the tree. One thing that's just a perennial surprise is that the depth of them. So if you think about it, this is a kind of contagion process. It's operating in a social network that, while it could be on billions of people, we know has very shortest paths between people, right? So the whole point of things like the 6 degrees of separation is that from any place where I drop information in, it could in principle take 4 or 5 hops and it would be essentially anywhere. So if this information was traveling on shortest paths, the tree should look nothing at all like this. It should look incredibly wide and incredibly shallow, and you wouldn't really be able to meaningfully draw it in any way. And just in every domain that one looks at, almost every domain one looks at, that is simply not what they look like. They go very deep. They're relatively narrow. You can easily find things that arrive in someone's inbox or on their timeline after 50 or even 100 reshares. And so one question is, what's going on there? And I'll actually pose this mainly as an open question, which a number of us in the CS community, also in the economics community through the work of Ben Gold and Matt Jackson, have looked at this question. But the sense in which it's largely open is that for many of the basic phenomena with these big networks, we have some very simple explanation for why it should be there, right? So, the basic reason 6 degrees of separation is there is that if everybody has, order of 100 neighbors and you have a billion nodes, then, log base 100 of a billion is 5. And that basically gives you the right ballpark estimate. We don't have a correspondingly sort of brute force simple explanation for why the trees are just constantly so deep. Some of the ingredients, appear to be, well, so obviously when I'm, sharing, I don't share it with all my friends. I share a meme with only a few friends. So it's certainly a narrower tree. But that doesn't really explain it, because even if I share it with 3 friends, to get 50 levels deep, you need, a branching factor of 3 is way more than enough. There's certainly a preference for strong ties. So again, this distinction between strong ties and weak ties was going to show up throughout the talk. It's not clear this is being shared on your network of all ties. Maybe it's being shared on your strong tie network, especially if it's a controversial or contentious piece of content. That too doesn't seem to produce the deep trees. Probably one part of it is actually the large heterogeneity in the rate of node response. So I send it to a few people. Some respond immediately. Some take a very long time, by which point the message has found other paths. And so one literature that's probably useful in thinking about this is actually the literature on shortest paths and graphs with random edge lengths, right? So think of this thing as traversing a graph, but there's a delay time on each edge. And this delay time is drawn from some distribution that takes very large values. And then I say, what is the weighted shortest path between, right, two nodes? What's the quickest path? Not the minimum number of hops, but the one that would actually get there the fastest. That actually is known in work, beginning with some work of Alan Fries and others, to actually produce relatively long paths. And that presumably is some large component of the explanation. One other thing that we've been thinking about recently, which some of these probabilistic contagion models can actually are surprisingly consistent with, is that this picture of a sort of one-shot view of information sharing, where the information gets dropped in at a root, it spreads, spreads throughout the tree through probabilistic contagion. One sort of missing picture there is that actually this information often recurs. It'll have a flare-up, an outbreak, it'll reach a lot of people, it'll become dormant, and then it'll start up again. And so in fact, in this ongoing work that I'm doing with Justin Cheng and Lada Dominic at Facebook and Yuri Leskovic at Stanford, you can actually look at some simple definition of what it would mean for one of these memes to recur. If you look at the sort of volume as a function of time, there are a lot of ways of doing this. You could have a generative model for when it's active, when it's not, or you could just simply threshold. You get basically the same answer no matter what you do, because these are very prominent spikes. And the point is, under any of these reasonable definitions, about 30 to 40% of Facebook image or video memes actually recur. As in, they go up, they get very active, they quiet down to near 0, and then sort of order of 1 to 2 months later, they flare up again and have these big outbreaks. And what's interesting is that the behavior of this actually is consistent with, at least at a qualitative level, what you might find from a simple probabilistic contagion model in certain macroscopic respects. So one interesting macroscopic property of this cascade recurrence is that it's sort of most prominent, most pronounced for moderate-sized outbreaks, right? So if the first outbreak is very small or very large, then conditioned on that, the expected number of future outbreaks is much smaller. If it's sort of medium size, sort of in this kind of 100,000 person range, that's actually when the conditional expectation is highest. And what's interesting is that's exactly what you would get if you imagine sort of a probabilistic model of the epidemic. And when you simulate this, in fact, you actually get shapes like this. Effectively, imagine what's happening is sort of I have some process like at random nodes at randomly spaced times, the meme is going to occur. It'll then get transmitted probabilistically across the links, right? So some underlying probability P, a neighboring node will accept it and pass it on. But after a node has seen it, their probability of doing it a second time is going to go way down, right? It could go to 0 or it could just go to some smaller number P prime, right? When you try this out, you see that even just sort of intuitively, you see what's going to happen. If I have a giant cascade, then the very first outbreak exhausts the susceptible population. Everyone now has a kind of immunity to it. Second outbreak can't happen. If you have extremely, small and extremely small initial outbreak, these things never get going, and somehow it's in the middle of these things. Okay. So this idea of trying to model what's going on, the depth of the trees, the recurrent behavior, I think that's one thing where there are a lot of questions that kind of underlying generative models of this sort of information propagation could be quite useful. I wanted to say a tiny bit about content. This will be the sort of one bit about content I'll mention, because there are a number of interesting questions here also. So if we think about the language, used in these things, right? We can always ask the question, this chain letter petition that I put up before about the invasion of Iraq, it was obviously, issued under compelling circumstances at just the right time. It caught some favorable set of initial adopters, whatever. But you do wonder, did the choice of language have any, what was the role of the choice of language? Or, perhaps in the framework of prediction, does the language used help us predict the success of the meme? If we look at, if I'm trying to build a model that's going to help me, say, predict how far will this travel, if I add a bunch of language features, is that going to help me in my prediction? Now, this has actually been looked at in a number of domains, right? Research on crafting messages, certainly, as with some of the earlier classical topics I mentioned, dates back to at least the middle of the 20th century. It's also been used in the economics and political science literature, for example, in crafting messages during presidential elections for getting out the vote, for example, right? So extensive use of an A/B testing framework to ask whether phrasing an appeal to get out the vote one way or another leads to more uptake. But we also see it online, and we see it for an interesting reason, which is there are many, many instances where a piece of content will be shared twice by somebody, actually. And we can actually, therefore, look at differences in phrasing. So there's some interesting recent work by Tan, Li, and Pong, where what they did was they looked at pairs of tweets where the same user, within 12 hours, had tweeted a link, and then they came back and they tweeted again with completely different text. It's not entirely clear why this is such a widespread convention on Twitter. It's actually remarkably widespread. Maybe people weren't satisfied with the uptake on the first one. Maybe they had a better way of saying it. It isn't clear. It is, in fact, the case, though, that there isn't a consistent first versus second does not give a consistent prediction as to which one's going to be more successful, right? So it's not that the first one is, even 50 plus epsilon% more likely to be successful, or the second one. But it does give us a nice framework for asking a very, very simple prediction question, right? Where I've somehow, as much as possible, kept the author constant, the payload constant, it's the same link, and the time constant, and I'm just asking which of these two actually got more uptake, right? So, and you can see what your own intuition is, right? So this is somebody promoting food trucks. The first time they say, I know at some point you've been saved from hunger by our rolling food trucks friends, let's help support them. And then they came back a little later and said, food trucks are the epitome of small independently owned local businesses, help keep them going. Similarly for the second one, which is someone in Britain who's extremely angry about work capability tests. And so one can build some kind of a model here using, using features of the language. And the interesting thing is that there actually appears to be signal in the language that actually gives us some indication of which is going to be more retweeted. So if you do this as a human task, right? You recruit volunteers and just give them these pairs and ask them which one is it. The human performance is about 60%, which again indicates there's some signal here relative to the baseline of just guessing between pairs. And the algorithm performance exceeds that, up to about 65%. And what's interesting is that actually, one recurring set of features that's quite useful here is the likelihood of the language used in the tweets relative to different sets of baseline language models, right? So, in fact, right, so if the tweet is closer to the style that the author generally uses, that's a useful feature of prediction. If it's closer to the baseline for Twitter, that's a useful feature. There's something interesting here also, which is, so the human performance is 60%, but of course, it's humans who determine which gets retweeted more anyway, right? It's the humans who were doing the retweeting. So one would think that if I collected a lot of human judgments, the majority should gradually converge toward much higher prediction accuracy. That's not a given, because the humans where we're asking them to make this guess are not the same humans who are actually choosing to retweet it. They're making this second order prediction. But it is the case actually, as you take majority vote among more and more of these human predictions, the accuracy climbs much, much above algorithm performance. What's interesting is this notion of looking at the effect of content. One can do this in a number of domains. And actually this 65% algorithm performance has been somewhat stable across domains that you would think were quite diverse. One other that we looked at was quotes from movie scripts, actually. You can ask very, very similar question. I can go through scripts from movies, most of which are online. I can take lines spoken by characters in the movies, and I can ask, okay, here are 2 lines uttered by the same character in the same scene of the same movie, approximately the same length, sort of next to each other. Is there signal in the text that might help me predict which of these is going to appear more on the internet, for example, right? So I do a Google search for these 2. If one is significantly more prevalent on the internet than the other, that's the one that somehow has more, made it out into the online world. Algorithmic performance is again, now it's roughly 64% using the best features we can assemble. Human performance has gone way up. In part, many of these things are part of the culture and people are using domain knowledge. But right, so we're imagining something just as with the tweets. The tweets exactly had the same payload. Yeah, but here you might take some scene from some movie like that many of you know, Star Wars, and ask, okay, which of these lines spoken by Alec Guinness is the one that entered pop culture, right? And the answer is one was infinitely more successful than all of the others. So these are the kinds of issues that one might look at if one thinks about, is there signal in the content? And I think what's intriguing here, from a prediction point of view is, the answer could have been yes or no. It could be that this, the fact that these aren't the droids you're looking for became popular was entirely somehow incidental to what was actually being said. In fact, this is a good example where if you see the scene, it's a completely, it's not that this is in any sense the punchline of the scene. But in fact, if you look over many, many instances of this, there are these recurring features. And again, often based on likelihoods relative to a base language model that's actually helping us predict these things. What's sort of interesting is that as we think about these textual fragments and how they spread, you start to think about the ecology of memes, right? There's always been this sort of metaphor, right? In fact, the word meme dates back to Richard Dawkins, who in a sort of pop science context was making the analogy between genetic elements, right, and cultural fragments that are transmitted. And and the point is these phrases or these other sort of cultural constructions, right? They have heritability, they have fitness, they mutate as they travel, and somehow those are the 3 basic ingredients. Now, again, when it was sort of first introduced, it was almost pedagogical or metaphorical, but with the idea that there is something underneath all of that. And I think what's interesting is that one can start to assemble the ingredients of an ecology of memes, right? Effectively, the previous 3 slides are talking about the fitness function for memes, right? There's something actually in the content that helps us predict whether they are going to be successful in this landscape of memes. And in parallel, a number of us on the computer science side have been looking at mutation of textual memes as they travel from source to source, right? This is sort of necessary if you're working on, for example, extracting quoted phrases from news. because even looking at things in exact quotes, one keeps finding small changes, right? So this is when Yuri Leskovich and Lars Backstrom and I tried to reconstruct the 2008 pre-election news cycle. Any one quote that you wanted to reconstruct, like Sarah Palin's quote about our opponent sees America as imperfect enough that he's palling around with terrorists who would target their own country. There were hundreds of different formulations of that through a combination of excerpting, misquoting from the media, and also just Sarah Palin said it many times, and she said it slightly differently each time. And so, when you think about this, we're starting to see the sort of outlines potentially of a fitness function. We're starting to see the outlines of mutation mechanisms. And even in this nice work that Simmons, Adamek, and Adar did, as they looked at mutation, they found that, just as with genetic material, there's somehow the functional element that changes very slowly, and there's the junk DNA of the quote, which changes quite rapidly as it's passed along, right? And so the rates, even within a single stretch of text, are quite differential in the rate at which they mutate. It would, of course, be, overreaching to say that we're anywhere close to actually having, the sort of formulation of a meme ecology, but I think it is sort of interesting that the outlines of the different ingredients that you would want are starting to emerge from this picture. Okay, so that's the halfway point, and that's a bunch of questions about social transport of information and the way social media has both, I think, helped enable it, helped transform it, and also provided us with a lot of ways of measuring what's going on and trying to make predictions about it. The second half I wanted to talk about, again, in the spirit of sort of an overview of a lot of these questions, this idea of maintaining our social ties across time, right, in the spectrum from strong to weak ties, and the way in which a detailed understanding of that is actually vital for a social media platform like Facebook if it wants to actually, give you a satisfying picture of the information coming in from your social neighborhood. Again, this picture of concentric circles where I want different kinds of information via my strong ties than I'd like from my weak ties. Okay, so if we want to think about maintaining social ties, it definitely helps to just have a kind of picture of, what does one person's network neighborhood look like in these kind of social media systems. This is a picture that I'm quite fond of staring at, actually, which I looked at a lot, pictures like this, when I was working on these kind of network neighborhood questions with two of my former PhD students, Lars Backstrom, who now manages newsfeed ranking at Facebook, and Johan Ugander, who's an assistant professor at Stanford. And the idea was, first of all, it's just, of course, conceptually easier to think about Facebook not as a 1 billion node graph, which in any real sense is incomprehensible to us, but instead is really a billion network neighborhoods, right? So for each person, this is one person in Facebook, and these are all of their friends. And I've drawn a link between each pair of their friends who are themselves friends, okay? Right, so everyone here is one of their friends. These links indicate friendship among their friends. And this is just a spring embedding. So it basically says, draw all their friends in the plane so that the centroid is at 0, the sum of the squared distances is 1, and the sum of the squared edge lengths on all the edges as they're drawn is minimized. And that's going to cause dense clusters of edges to all collapse down. But again, subject to the constraint that the centroid has to remain 0 and some displacement. Okay, so, and essentially, some of you in the audience may have visualized your social network neighborhood on Facebook at some point. If you have, it's a safe bet that it looks basically like this, because all of our network neighborhoods look like this. Having scanned through thousands of these pictures, I can relatively safely say that. What are the features of this? So there are these different parts of your life, right? All these people know each other. Many of the people know each other. So this is some facet of this guy's life. These are actually his coworkers. This is some other facet of his life. These are his old friends from college, as it turns out. Somewhere in here is his family, a sort of smaller cluster of people that know each other. Right? There's some sort of hobby that he belongs to. Actually, one of these was a cluster that actually grew into a startup company that he founded with some friends. And when you went back and looked at this 2 years later, that one had inflated quite significantly. There are all these things. And sort of like any kind of aesthetically compelling image, Lars and Johan and I would kind of go back to this periodically. And every time you go back, like any of these things, you sort of see things that you hadn't seen before. But the first question, of course, is just how should we characterize, if we have 1 billion of these, is there some ambient space that we could put them in? And this was a really interesting question that kind of, I think challenged our kind of thinking about generative models for networks, because in a sense we don't, we're only at the beginnings of having reasonable models for things that have this kind of structure, right? So formalisms like the stochastic block model get at certain aspects of it. But as a first pass, we just want to understand what's there, right? Can we just sort of look at that? And so in addition to what's there, we'd like to ask, how does it depart from the simplest baseline models, right? So before we get to more sophisticated models, we could just ask, what are its features relative to, say, a purely independently generated random graph, something like GNP, as it's called in the random graph literature, where I just put down n nodes, and for every pair of them, I connect them independently with some probability p. Right? That's sort of the simplest thing you would do if someone told you to generate a random graph. And the deficiencies, so this dates back to this celebrated work of Paul Erdős and Alfred Renyi in 1960, although they were actually not the first to actually, they were the ones who popularized it, though not the first to actually suggest it. The sort of deficiencies of this as a model of almost anything are well documented. It's hard to blame Erdős and Renyi, who invented it for completely different reasons. But first of all, it produces it doesn't produce these very, very wide disparities in the number of neighbors that a node has, right? The degrees are concentrated. And also, it's not nearly as rich in triangles as real social networks are, right? I mean, one of the recurring features of these things is how many triangles we see in these networks, right? And it's really because of many, many things, underlying notions of homophily, node similarity, and also just the process that sociologists call triadic closure, where if two people have a friend in common, they're going to form links between them, and the graph will densify. Okay. So if we wanted to sort of tabulate what's there, how does it relate to this underlying GNP model, what are the deviations that we should be interested in, one thing we could do is just try to find a simple short vector that describes each of our billion node neighborhoods, right? Something very simple to compute. And one that's actually been used in many, many different domains, in sociology, in computational biology, in computer science, in pure math, is this notion of turning a graph into a vector of its small subgraph frequencies, right? So for some small number k, and for every possible k node graph H, and here k is very small, like 3 or 4, right? So for every possible 3 or 4 node graph H, let's say f sub g of H is the fraction of k node sets that induce a copy of H. What do I mean by that? So I go back here, and I take my graph that I had before, and I look at every possible 3-tuple of nodes, and I see that for this 3-tuple, there's an edge here, but no edge here. And then I go to my set of all 4 possible 3-node graphs, there are 4 of them, and I add one to this thing, because it's a copy of that. Right? And I just go through and I tabulate. And I end up with some vector that clearly in no sense describes this graph, but is some sort of compact set of features that may be useful in thinking about this. Again, right, this is sort of very, very first pass on trying to sort of tabulate what's there before we think about what models might look like. Similarly, for 4, there are 11 possible graphs on 4 nodes. There's absolutely no reason why you should know that fact, but there are. And I could go through all possible 4 tuples and just tabulate. Okay. And one thing actually that is just sort of interesting to do is that for the 3-node graphs, there are 4 of them. These 4 fractions add up to 1, so there's 1 degree of freedom I don't need. So it's really, there's 3 degrees of freedom here. And so I can actually take this set of all node neighborhoods on Facebook, and I can actually plot them in a cube, right? And actually, I could ask what that looks like, right? So I take the cube. I have 3 axes labeled by 3 of the 4 graphs. I'll just take out the last one as the missing degree of freedom. And then I just, I put in all of these things. And this is actually what the space is. And actually, there's sort of 3 different things being shown here. So there are a combination of network neighborhoods, and then also Facebook groups we also threw in, which have similar, as it turns out, properties. They also lie along this. It's interesting, and as soon as you see this, you realize there's sort of, you of course ask, only part of the space is populated. Why is that? And what's interesting is there are 2 fundamentally different reasons why only part of that space is populated, right? One is a social reason, which is certain configurations just don't tend to arise in your network neighborhoods. And the other is a purely mathematical reason. There are actually some vectors I cannot produce with a graph. Right? So in fact, it's an interesting theorem in extremal graph theory that the largest fraction, right, if I try to build a graph and have as many of its 3 tuples be this as possible, the maximum number I can make is actually 3/4. I can't have all 3 tuples be that. I can have all 3 tuples be this by putting in no edges. That's that corner. I can have all 3 tuples be this by putting in every edge. That's that corner. But this corner I can't get to. That's a mathematical fact. It has nothing to do with how people form social networks. But the underpopulation in this part of the space, for example, is a purely social human fact. It's basically saying that people simply don't make network neighborhoods where I have all the people over here of type A and all people of type B, and everyone of type A knows everyone of type B, but no one of type A knows each other, and no one of type B knows each other. Right? That's essentially the complement of what we actually see in our real lives. My coworkers all know each other, and my friends from college all know each other, but they don't know each other. Right? And that gives us things that are sort of right in the thick part of this distribution. But the complement of that, where each of my coworkers knows each of my college friends, but otherwise they don't know each other, simply does not happen. Right? And that's fact about humans. Graphs, no problem making graphs like that. And so this gave us some way of thinking about this. It'd be nice if I could actually show you kind of some sort of polytope or other region surrounding this cloud that says these are the mathematical constraints on graphs. But that's actually a monumentally hard problem in graph theory, of which very little progress has actually been made. Some of the nicest results were actually proved by someone in computer science here at University of Chicago, Alexander Razborov. But simply showing you the true bounding box based on what graphs can do is a wide open question. I could also ask, where's GNP in all of this? Right, so GNP, which was again, put every edge in with probability P, has this one, right, so there's this one free parameter, P, which is the density of the graph. And as I vary P, I get some kind of parametric curve through the space, right? Because as the edge density changes, all four of these coordinates change. And when P is 0, I'm here, no edges. When P is 1, I'm here. But in between, it's following some kind of, as it turns out, a kind of serpentine cubic curve that sort of runs like a nerve through this cloud of points, but not completely, right? And the cloud of points deviates from the GNP curve in the direction that you'd expect, namely in the direction of triadic closure, right? The real ones have too many triangles relative to what GNP predicts. So as I said, it's an interesting question to think about what are some better generative models for what's actually going on in these graphs, and can I actually start to think about those? Lars, Johan, and I have been thinking about these kinds of questions. I'll tell you one thing, one thought that we have where there's a lot of open questions here to really analyze what's going on. It feels like, okay, if we believe triadic closure is certainly one missing ingredient, let's think about a model that has edge formation and also has triadic closure. So instead of GNP, which just says flip a coin simultaneously on every edge, let's imagine a graph being generated, say, by a continuous time Markov chain. So what I'll do is I'll put down n nodes, and then I'll have these alarm clocks on every pair, which are going to ring. And when the alarm clock goes off, say at rate gamma, if there's no edge, I put in an edge. And when there's an edge, the alarm clock rings at rate delta, and the edge goes away. All right. Now, if I only had that, I would actually have just a very complicated way to write down GNP, because every edge would be going in and coming out, and basically there'd be some long-run limit, and the edges are independent. So also, for every structure like this, I'll put one more set of timed processes, right? So one more set of Poisson processes, which is whenever I have U whose neighbors are V and W, but V and W are not neighbors, that's the sort of signature for triadic closure being able to happen. There's going to be this process of rate lambda, and it's going to add this edge. There won't be a corresponding process in the other direction because there is no kind of sort of primitive for triadic destruction that we want to model. We simply want to model triadic closure. Okay, so then I get this continuous time Markov chain. Now, this is actually sort of hard, appears hard to prove things about in general. One can write it down, say, if I were just studying 4-node graphs in isolation, which is not what we're doing. We're trying to study big graphs. But this definitely gives some insight as to why this is an interesting model. So for example, this is the transition matrix on it. It certainly gives some insights into why certain structures are just unbelievably rare in real social networks. Like the induced square is, of all the 4-node subgraphs, that's the least frequent one. And it's actually true. In your everyday life, squares are very rare, where these 4 people know each other in this pattern, and these edges aren't present, right? I mean, I see this in my own life, even like while I was working on this paper, I was walking with a colleague, we passed 2 people. I knew the one on the left, and he knew the one on the right, but we didn't know the other one. And we thought, isn't that weird? That's kind of, and it took me another block to realize it's the square, right? I mean, that's exactly why, And the reason is because the square under this continuous time Markov chain view is really like, it's like an unstable molecule that's hard to build and breaks down as soon as you build it, right? Because to get to it, I have to get to here, and then rather than close one of these triangles with one to close, I have to build this edge, which is less likely. And once I'm here, then there are these edges that want to form, and it immediately breaks down. Okay, and so what's interesting is that I have basically 2 parameters. I have the ratio of edge creation to destruction, which is essentially the role of P in GNP. And then I have lambda, the rate of triadic closure. And if I were just thinking about 4 nodes, in fact, with these 2 parameters, one can start to actually fit the empirical frequency of these 4-node graphs. But again, sort of proof of concept, because we're not interested in studying 4-node graphs. We're interested in studying these large graphs and think about the kind of macroscopic properties that processes like this have. And there, I think there are a lot of interesting open questions to think about. OK. But let me come back sort of as the last thing to focus on. The actual algorithmic question of looking at these network neighborhoods, right? These things that we stared at with the clusters and the coworkers and everything, and trying to figure out, how do I create the concentric circles I was talking about, right? The strongest ties, the moderately strong ties, the weaker ties. Can we recognize these from the network structure? Because again, this is a central issue in trying to rank the content. And again, the fact that I was doing this with Lars Backstrom sort of made these questions particularly salient, because this is sort of what he needs for his day job running newsfeed ranking, where the whole question is, out of the 1,500 or so pieces of content that your friends produce every day, which subset should the algorithm actually show you, right? Right. If you think about your inbox, once you pass 100, it gets very stressful. You don't want to see 1,500 things when you log into Facebook. The question is, what is the subset that you actually want to see? And if I knew something about the nature of your friends and the connections, that would tell me something. So we sort of had this idea, let's try ranking, and this is an activity that people have done both in sociology and computer science, try ranking the ties by strength, by this, what sociologists call tie strength. And here too, triangles obviously play a key role, because in some sense the gold standard measure, if I'm just looking structurally at the graph, for tie strength, what's a good proxy for tie strength? The number of triangles containing this edge E is, if you have to write down a single number, that is certainly a very good heuristic, because it's basically the number of mutual friends shared by E's endpoints. Right? So if you're good friends with somebody, over time you acquire a bunch of mutual friends, and that becomes a signature of a strong tie. Whereas someone you barely know, who you met a few times, but now you're friends on Facebook, you might have 0 friends in common. OK, so embeddedness, that's a number I want to think about. So just so we all get definitions straight, right? Here's an edge VW, and they have an embeddedness of 4 because they have these 4 mutual friends. And you can say, all right, just to understand what's going on, let's take these network neighborhoods we have, and let's just rank all the neighbors by embeddedness and see what's happening. And what's nice is, for these computations, which seem innocuous enough but are sort of happening at Facebook scale, what's nice is that because I was doing this with Lars on the newsfeed infrastructure, one can actually sort of piggyback some of these analyses just on every page load that you do with newsfeed, right? So someone shows up, loads their newsfeed, it ingests all of this information, and then we can sort of put some lightweight analysis on top of it and try to figure out what's going on. OK, so what if we rank neighbors by embeddedness? So this is one of these ideas that the instant you try it, you realize why it's not going to work quite as well as you thought. Right, let's go back to this picture. The point is, for this person and most people, the most embedded people are all going to come from this gigantic cluster. Just pick the largest cluster. They all know each other. And so, every random coworker this person has is going to show up as like this really good friend under the embeddedness measure. And yet if you ask them, they'd say, yeah, I know them, but they're a coworker and not one of my closest friends. And surely in here, family members, there's a sibling in here maybe, surely there's all these close friends, but they simply can't compete. There's just not enough other people around here to create the density of triangles that's going to make it rise under the embeddedness measure. And so I mentioned that, over a few years thinking about this, we've gone back to these pictures, and every time we stare at them, we see something we didn't see before. And in this case, you go back and you notice this thing that should have been obvious from the very beginning. This node down here at about 7 o'clock. This is a very interesting node, right? So it actually has reasonable embeddedness, not quite as high as here. But it has these edges that just go out to all these different clusters. There's something unusual and kind of eye-grabbing about that node, even just in the spring embedding. And that turns out to be the spouse of the person in the center. Right? This line sort of stands out there, even visually. And so we found ourselves asking a question, because embeddedness was just not working. There was a bunch of missing ingredients there. We found ourselves asking a question that we didn't set out to ask, but was sort of, kind of useful for organizing our thinking on this, which was, if I give you a Facebook user who's in a relationship, right? They've declared on Facebook, I'm in a relationship with this person. Can you find the relationship partner from just the network structure alone, right? Again, not the question that we started with, but in some sense, it's, I guess we're sort of fond of doing this when we're designing algorithms, that you figure out where your techniques aren't working, you set yourself a challenge problem, you say, can I actually find this thing, right? So it's sort of, it's a kind of prediction as used for detection, right? There's a ground truth hiding in this picture. Can we find the ground truth? And it's a very concrete problem. The input's a graph. You can use whatever graph theoretic algorithms you want, and there's this hidden label that I'm going to tell you, right? Okay. So the idea, of course, is that we have a lot of room to maneuver here because embeddedness is just about counting mutual friends. It was sort of the simplest possible thing you could do. The instant you start thinking about it, you realize there's many other things I could do. So for example, here are two cases where an edge VW has an embeddedness of 4, right? But arguably, intuitively, this is the coworker signature, right? Those 4 friends are all connected to each other, right? They all kind of come from one giant cluster network. Whereas here, this is a kind of more interesting case with embeddedness of 4 because these two people know each other, but they don't know this person, they don't know that person. So on the right, V and W are sort of like together this bridge between different parts of your social circle, right? And so there are various ways to say this, but like, for example, if I'm V, my relationship with W cannot be explained just by any one cluster in my network. It sort of fits into multiple clusters. In a way, it is a type of bridging or brokerage, to invoke terminology made famous by another University of Chicago faculty member, Ron Burt. And I think bridging and brokerage sort of was kind of a clue that got us thinking about this. What's interesting here is that it's not bridging or brokerage between groups by one person, right? It's really by the pair, right? It's the edge that's actually playing the bridging role, not the individual node. And because the edge is doing it, it implies a certain kind of strength to that edge. Okay, so what does that suggest? So if I'm trying to measure bridging, we can sort of think about, if I have a graph and I want to say, here's a structure, to what extent is it kind of bridge-like? There are certain natural algorithmic formulations that one thinks of in that way. And many of them derive from the idea of asking, what would the graph look like if I took the bridge out, right? One way to identify bridges is to say a bridge has the property, conceptually, that if I remove it from the structure, the things around it have changed a lot. And a non-bridge has the property, if I take it out, the things around it don't really notice. So one way to operationalize that would be to say, okay, so let's say I have edge VW, I have a set of their common neighbors, C sub VW. And I'm just going to take all pairs in VW, and I'm going to look at the sum of their graph theoretic distances after I delete both V and W. Before I delete V and W, everything has distance 2, because in hop count, they all go through V or W to get to each other, right? So CVW is a big set, all at mutual distance 1 or 2. Some of them are distance 1, and the rest are at 2. After I take it out, then I might have some long paths. Now, I have to, and I'll call any measure of this form a dispersion measure. So this is the dispersion of the edge with respect to the distance function d, because basically how much it disperses the common neighbors around the outside. Now, I need to be a little careful in a few ways. One is I should use a 0, 1 value, or I should use some kind of bounded metric, because it could be I take out VW and one of these distances goes to infinity, and I don't know how to handle that in my sum. So I'll cap the distances. It's also not, I may want to do some normalization by the size of the set of common neighbors, because again, since I'm trying to have something that is sort of giving me different information from embeddedness, one problem is that if I just have the pairwise sum, that's a quadratic number of terms being added up, and that can actually overwhelm whatever it is I'm trying to find, because it's just sort of conveying the embeddedness through simply the sheer number of terms in the sum. So I could do some normalization there. So one can try a number of different measures here. And actually, I'll point out that, this actually sort of gets at kind of an interesting methodological issue in thinking about this. We're sort of on the trail of trying to find a measure that's going to help us find this particular kind of node. We have the raw data of essentially the adjacency matrix of the graph, and yet we're trying to sort of hand create these measures. And you could ask, why are we doing that? And really, it is because, our ability to construct meaningful features for graphs is still quite limited, right? And it's, and I think Dave made this point nicely yesterday morning, that, I mean, with graphs, I think there's a lot that we don't know about how to find just sort of, robust familiar features that capture this. And so one is in the realm of still, I think we're still in the process, and, this kind of work illustrates how one still finds sort of new things to add to the vocabulary of features that are useful, right? So we're sort of thinking about this sort of hand-created measure. But it has this very simple functional form, right? It's a sum of distances when you remove things normalized by the total size of the graph. But I think it is an interesting question, sort of, knowing what we know, could one have somehow derived this in a more kind of black box fashion, just sort of dumped in the adjacency matrix and sort of out came a measure that did this? I would argue we're actually relatively far from doing that with graphs for these particular kinds of questions. Okay, so that's our measure. We wanted to see how does this measure do. So for evaluation, right, we took 1.3 million Facebook users, sampled at random, subject to the following properties. They declared a relationship partner in their profile. That's a symmetric thing, right? You say you're in a relationship with someone, they get a notification, they have to agree, and then now you're both there. And to eliminate the sort of edges of the distribution, they have between 50 and 2,000 friends, and they're at least 20 years old, which we put in for all sorts of reasons. One of which actually is that, so one known failure mode of the relationship partner field, at least, sort of historically, is that teenage girls often, for example, say they're married to their best friend in high school, and that just throws everything off. So, but if you say at least 20 years old, and you randomly sample such as that, certain kind of checks that we did seem like these really are the relationship partners to the extent that we can tell. Okay, and then the idea was, let's just evaluate. Let's say we'd like to take the user V, we'd like to rank all of their friends by various metrics, and then we'd like to see how often is the most highly ranked person the actual relationship partner, right? So this extreme precision at one measure where if I give you one guess, what's going to happen? So the competing metrics, so the embeddedness, this gold standard from the theory of social networks, the dispersion, which I just defined for you, and then of course, when you load someone's newsfeed, you get a whole bunch of activity metrics about them, what they've been doing. And if some of those are going to be more useful at finding relationship partners, we should know that, right? We should be using the structural measures if it's helping us, but we should understand if it really is helping us. So, what is it that we know about someone at the moment that they walk up to newsfeed? For each other person, how many times have they commented on their content? How many times have they liked their content? How many messages have they sent them? How many events have they checked in with them? All of these, how many photos have they been co-tagged? How many times have they viewed their profile? A wide range of these activity features that are not about the network structure, but just about your interaction with that person. And surely that conveys information also. Of these, now ultimately, as I'll point out, we took all these features and we dumped them into a gigantic black box machine learning algorithm, and that of course does better than any one feature individually. But it's useful to see which individual features are powerful. The two at the activity level that are most useful, as it turns out, one is the number of photos in which V and W are both tagged, right? So if you're regularly, showing up together in a photo, that indicates something about the strength of the tie, obviously. And the other is actually a number of times that V viewed W's profile over the last 90 days. Because it turns out when two people are in a relationship, they just do a lot of profile viewing. Okay, so you got that. And so the question is, for what fraction of all users V is the top ranked W the relationship partner? Okay, and so now I'll put up a table like Dave explained that in talks where you're doing prediction, you have to have a table that say we're the best, so I have to have that table. So let me actually walk you through that table, because the kind of, in this case, no one thing is clearly the best, but we do see some interesting things. So one, again, everyone has at least 50 friends here. I'm doing precision at the first position, right? I'm making one guess. So the baseline guessing rate is at best 2%. So certainly the question is, how well are we going to do relative to that? And the surprise was just, first of all, the absolute number, right? Making one guess with the dispersion ranking, more than half the time is finding the relationship partner. Right, so that thing that jumped out of this visually in the lower left corner where you could just see it in the spring embedding, that's jumping out to the dispersion measure also. Embeddedness is doing fine, right? A quarter of the time, more than an order of magnitude greater than the baseline guessing rate, it's finding the right thing. But you get another factor of 2 improvement from this. And this is actually, again, at the level of individual features, finding it more than a ranking based on, say, photos, profile viewing, or any of the other behavioral metrics. Which again says something interesting about having the right graph theoretic definition, right? If I had simply started with the sort of bland question, which is more useful for finding relationship partners, structure or activity, and I had equated structure with this embeddedness measure, I would have said the activity measures are doing better, and I would have been wrong because I would have had the wrong definition. It also, of course, makes even more vexing the question of, but how do we know this is the best graph theoretic definition? And I think that's a very intriguing question that we don't have a great understanding of. We can certainly do better on structural measures do better for finding married couples than people in a relationship, right? So this was people in a relationship, people are married, people are engaged. Whereas actually for people in a relationship, the single best feature, if I'm just looking at them individually, is actually the profile viewing, more than the structural measure. I'll actually say more about that, how you can kind of partially interpolate between these two things rather than just treat them as discrete categories. It's actually easier to find the relationship partners for one gender than the other. Right? So that person at the center where I'm trying to find the relationship partner, I can do better if they're one gender than the other by about 10 percentage points, actually. And so first, just for gender at the center of the graph, it's actually about 10 percentage points easier to find, 5 to 10, when the male user is when a male user is at the center. Right? In a sense, when a female user is at the center, there are more other nodes that show up highly in the dispersion measure along with the relationship partner. Yeah, so we also looked at same gender or opposite gender relationships. There's a big imbalance on Facebook in that most of the relationships reported on Facebook are opposite gender relationships. For female users, the performance was relatively similar. Opposite gender, same gender. For male users, actually, one had some different. Actually, no, I have that backwards. Yeah, for male users, there were actually some more pronounced differences. So there's some interesting things there, which I'm happy to talk about. Good, and then right. So, although again, as I said, it's sort of a vexing question how to derive better graph theoretic measures in some sort of black box fashion. It's certainly easy to combine everything once you have the graph theoretic measures in a black box fashion. So we threw in these graph theoretic measures, many others. I mean, we looked at many different variations of dispersion, but also betweenness centrality measures, brokerage measures, lots and lots of things. We put all these together, and then you can get about roughly 70% accuracy in the first position. And when the algorithm is wrong, about a third of the time, the thing it's finding is someone who's listed as a family member, right? So a parent, an adult child, a sibling, and so forth. I mean, it's sort of interesting to think about, in the sense that dispersion is really about you and the relationship partner share many different foci in your network neighborhood. The same is true of siblings, for example. And yet it's funny to think about how those two network signatures came about by very different means, right? Because I think we're almost at the end, right? 3 minutes? That's good. Great, yeah. I think, so the sibling has links into many different clusters in your network neighborhood because they met those people around the same time you did. They grew up with you, typically. Whereas the relationship partner is almost sort of does it in a more time-traveling kind of way, right? They've been introduced to all of those groups, but this effect on the network is sort of the same. Okay, I said you can sort of partially interpolate between married and relationship. One way to do that is to look at the time since the relationship was first reported. Now, this is a somewhat fraught activity because this is since it was reported. I mean, you may have been married for 10 years, you get on Facebook, and now you announce that you're married. That doesn't mean you just got married. So there's obviously a number of issues there. But as time unfolds, one does see, there are sort of more and more people as we move to the right who really that is the age of the relationship or some proxy for it. And we see that the structural measures are going up, the photo measure is going up, profile viewing is going down actually over time. Even more pronounced with relationship partners, right? So for new relationships, profile viewing, just the person in the first position there has enormously high accuracy. It goes down. The structural measures, of course, climb as the social network structure kind of conforms around the relationship. The two actually cross in predictive accuracy, which is a more kind of not clear whether that's a really significant moment, but around the 12-month point where, and there are certain things we don't understand at all here, which is there is no sense in which being co-tagged in a photo equals your dispersion measure. Yet for relationships, the two climb almost in lockstep in performance as we move over time, which again I think is largely a coincidence more than anything else, but intriguing. So this told us something, right? So as I said, we set out to do this because there was something we weren't understanding from simple measures like embeddedness. We wanted to understand them better. We set ourselves this challenge problem. We made up some different network measures. The effect was actually, in the process, I think we did learn something about network neighborhoods. I think we sort of enriched even our conceptual picture of what these neighborhoods look like. Because at the start of this work, if you had said, what do I think someone's network neighborhood looks like, I would have drawn you a schematic picture like this, which was to say, here's the node V at the center, and there's sort of a constant number of relatively homogeneous clusters, the coworkers, the friends from college, and so forth. Thanks. Yeah, actually, conclusion is right after this slide. But in fact, it's more complicated than this, right? It's really, if we want to think about models for what network neighborhoods look like, we really want to think about a constant number of homogeneous clusters plus a constant number of nodes that sort of defy classification. They're sort of sprinkled in there. And what's interesting is when I was thinking about this picture, I sort of thought back to something I'd heard Lotzi Lovaas say about 15 years earlier. He's a very eminent combinatorialist mathematician, who said that many sort of powerful results in graph theory, assert roughly that every graph looks roughly like a constant number of big pieces of relatively simple complexity together with a constant number of small things of very high complexity. And there are sort of a number of famous theorems in graph theory that decompose graphs that way, right, into sort of large pieces of simple structure and then a few very complicated small pieces. And effectively, empirically, that's sort of what this is doing. And so I think that's sort of intriguing. OK, so let me just wrap up. As I said, I sort of bundle all this into conclusions. I guess the point is with social networks, it's been this sort of exciting notion that we're seeing all this information largely for the first time, and able to take definitions that we've seen in the social sciences, from the theory of social networks and elsewhere, that have been extremely clarifying in our thinking about tie strength, about the organization of social network structure, about the way information flows, and some of them, once one actually works with this data, sort of are good heuristics, but clearly can benefit from some refinement. So I think there are the questions about finding the right frameworks. It's sort of hard to have a talk like this without at least putting on the agenda the question of the dangers of assembling this much personal data in one place, right? If you're looking at this and thinking, just sort of how much data about people went into doing this, that's certainly a reasonable question. But I think there's really an opportunity for sort of the intersection of all these communities that we see represented at this conference, computational and mathematical aspects of the information sciences and the social sciences, to really have a big effect in informing the next steps in all these questions. Thanks very much.
One high-level thing is, do we think of the thing that we're trying to learn about is the Facebook social network, or do we think of the Facebook social network as a measure of real underlying network? So your relationship thing is an example of that. But
right.
It seems like for the second problem, there's a whole other set of things, like different nodes have different propensities for their links to get reflected on Facebook.
Yep, exactly.
Use Facebook to different degrees, or certain
so
college friends are especially likely to get tagged with Facebook relationships because those are kind of easy to find.
Right. So I think that's an interesting tension in all this work. In part, I think it reflects an interesting tension in the actual workflow on these problems, where many of them are motivated by a bunch of computer scientists trying to make the online experience better. And then you're going to say, we want this to function better as an information processing system. We're going to use the features that we have there. And then part of the question is, are we in the process learning about things in the offline world? One thing that I think was, a sort of intriguing feature of the relationship partner question, as opposed to a question that say, who do you share the most content with, which would almost be a purely Facebook question, that the relationship partner was this kind of cross-connect between the online world and the offline world. Again, to the extent that I would say, to the extent that one believes we had a fair amount of confidence that these really were the real relationship partners, not just sort of some artificial universe. So I think it's a very interesting question to think. Anytime we ask one of these things, what is the linkage between this? It's also the case that lying beneath the surface, of course, that these systems are algorithmically constructed, which means when you're using features from them, you're also using features that came from the algorithms that produced them, which is an extremely daunting prospect that I think, again, the sorts of communities represented here, I think, have given a lot of thought to those kinds of questions, and they're very, very interesting ones.
Closure of triangles in particular.
Exactly. Facebook's creating the closure of triangles, exactly, because it's a feedback loop where if you believe in triadic closure, you put it in as a feature into your link recommender, which then recommends links. And so, in some sense, there are a whole bunch of questions you can ask on Facebook where the question is almost self-referential because you're asking, what have I learned about the Facebook algorithm? We've tended to try asking questions where the endpoint is something that we believe has some validity in the world, and then we're asking, how does the process by which this was constructed through all the complicated ways in which it was provide features that's telling us something about the outside world? But I think that's always a tension in all this work. Yeah.
Kind of a high-level question to connect to yesterday's talks and discussion. So if you want to estimate an opinion or a treatment effect of some sort, and you want to do it from the social network, if you are Facebook, right you're the company, you can do randomized sampling.
Yeah.
Right, but if you're querying the network or walking the network, you're going to get very biased estimates of the, the opinions or the treatment effects.
Yeah.
Can you comment on any recent work that looks at trying to, de-bias estimates you would get from walking along the graph?
Right. So that's a very interesting question, and I think one sees a number of communities that have looked at this. One certainly sees it in the sociology literature, like some of the work that Matt Selganik and Sharad Goel did on trying to understand some of these respondent-driven sampling methods. One sees it in the computer science literature, looking at random walk sampling method. Carter Butts, that's sort of the intersection of these literatures. And I think, a lot of these things, certainly start from this idea that if I'm doing a random walk on the graph, for example, to assemble nodes, I'm sampling from the stationary distribution, which is going to be degree biased and sort of in a very simple functional form. And so the question is, to what extent can I correct for these degree biases? And I think, there's also been some nice work, Dimitris Akliopoulos, Aaron Clausett, David Kempa, Chris Moore, looking at when I have partial information about the network, I'm going to often it's going to look denser, closer to where my walk started. And so the question is there some kind of a correction for the degree bias, given that I may not be seeing the entire picture there? So that's also, I think, been some interesting things. But yeah, I would say it's still, in some sense, it's largely. I think there's a lot of work left to do there. But I think those have certainly been, there was sort of a first insight about this. That my goal is to take a random walk, de-bias the role of degree in the stationary distribution, and then the second one of trying to actually look at the transient effects of the walk is going to sort of not mix, and so it's going to stay near a starting point. Yeah.
So early when you were talking about essentially these opinion dynamics, it looked like you're effectively fitting these log normals or something, to approximate that within this attention space, and then you talked about features of the things that are going out of the productive elements. So to what degree is there work that takes the other side, right? So the degree to which the environment itself, so like an old growth forest that's really dry is like ready for a forest fire, right? So it seems like obviously it's complicated because there's an environment that's pretty big, right, to sample from, but it also seems like even the distribution of features like likes and not likes, right? The thing that essentially get exposed to the thing probably, are likely to be predictive of the length or longevity of that curve. So to what degree do you get either internal to the exposures, like positive or negative things, or the environment itself predictions on the length of these attention cycles?
Yeah, so it's a good question. I mean, at sort of the most basic operational level, one certainly gets a lot of signal out of, say, the reaction to these things. That gets back to the question you were asking, that if one just did a pure question about how successful are these things as a function of, say, the community's reaction to them, since those are also signals going into newsfeed ranking, again, I'm seeing the effect of the algorithm. Less so on Twitter, for example, right? So the extent to which these features have meaning or not differs greatly between platforms. Since Twitter is largely unranked, your timeline is just a fire hose of tweets, there some of the incidental community reaction to it, since it's not going into the timeline ranking algorithm, is potentially giving me information that stands outside it. I think the other point that sort of I think you're making is that, when we think about, how successful is this thing that I'm sharing going to be, there's something about the sort of ambient readiness in the community, which is going to be a function of what everybody else is saying and how much it conforms to that. Certainly when right, I mean, certainly when I've talked with journalists about, these kinds of questions, for example, and I'm sure a number of you have had the same experience, that, right, they sort of think in terms of, is this story compatible with the surrounding ambient conditions, and it all happens in the fit between those two things. I think there hasn't been as much, certainly, algorithmic work on the computer science side saying, okay, here's my sort of baseline picture of, the sort of world's, baseline model for this topic, and then this is what this is adding to it. But I think, it'd be interesting sort of to see potential connections with work going on in other communities, because that's not something that it's an idea that's latent in the computer science literature on this, but hasn't really been acted on.
Since this type of research is mostly descriptive, and I was wondering if there are some emerging applications that are on the prescriptive side.
Yeah, so I mean, I guess it depends exactly what descriptive means. I mean, in some sense, what this is sort of an accumulation of algorithms that are sort of going into the kinds of systems which are ranking content, for example, right? I mean, so we could think of, like, what is the core application for some of these things? One basic picture of a lot of these social media platforms is they have this gigantic inventory of content produced by their users, and they're essentially trying to sort of figure out what to then present, right? And that dates back to search, for example, which had a gigantic inventory of web pages and wants to know what to show in response to queries. And somehow that notion of this huge amount of content coming in, and now there's a curation and filtering process going on. I think it's sort of common to many, many of the applications that you see. And so these sorts of algorithms are kind of central to those sorts of activities. But I think it's interesting to ask, what else in the world sort of either has that structure or, to the extent the algorithms have use here can also play roles there. All right, thanks a lot.